Welcome students to the first video lecture of Unit 4 that will be discussing random variables. Now, the first topic we're going to talk about are discrete random variables. So let's dive in. First, we'll start with some vocabulary and clarify what these terms mean. First up is the term random variable, and we usually represent it by a capital letter. Now, this random variable is a numeric measure of the outcome of a probability experiment, so something that deals with chance. A discrete one is either finite or countable in terms of its values. Later on, we'll be discussing the continuous random variable, but that'll be in one of the future videos, not this one. So let's stick with the probability distribution of a discrete random variable x, and we're going to lay out some rules to ensure that what we have is indeed a probability distribution for a discrete variable. As you might remember from probability, when you add up all of the probabilities of all the possible events, the total sum should equal 1 because there are no other possible events. And if you sum up all of them, then there's a 100% chance that something will happen. Now, each individual probability by itself must fall between 0 and 1 inclusive. So again, I have them reiterated on this slide. If you hadn't had a chance to familiarize yourself with the vocabulary, it's presented here again. So clearly, the definition of a discrete random variable and the description of a probability distribution are critical for this lesson. So take a moment to reread them. Now, suppose we toss a coin 3 times. Now, in the previous videos, we did a coin toss and looked at the results. In this case, we're going to toss 3 of them, and we're going to record the number of heads for our random variable x. Now, we're not going to write down what we see. We're just going to count whether or not we see a head. So when you think about this, what are the possible values for x? You can take a moment here and pause the video and think about it. So you might have realized that when you look, you might see no heads, which would give you a value of 0. You might see exactly 1 head, which would give you the value of 1. Or perhaps you would see 2 heads in any of the coins, and that will give you a value of 2. And if all of them come up heads, then your value for the number of heads will be 3. Now, the probability distribution would look like the following. You would put each of your values of x on the left, the frequency of that random variable, and then the relative frequency, which is the probability of that random variable. This looks a lot like something we've done before. So let's dive into an example that we've done before. Suppose we are looking at frequency distribution tables. So we did frequency distribution tables. We've done relative frequency distribution tables. Now recall when we did a frequency distribution table. In this case, we have an example of ideal number of children. So if that question was asked for 900 Americans, they responded in the following ways as to how many children would be ideal. So we can draw a relative frequency histogram for it once we get our relative frequencies. We'll also be able to find the mean by multiplying these 2 columns together and dividing by the total of the frequency. And also remember, we used Excel to do that grouped table data and the really complex calculations for the standard deviation. So we're going to utilize all those skills we learned in that Excel workbook on this problem to get an understanding of probability distribution and how it relates. Also recall when we talked about probability, we related probability to a relative frequency. So there's a very strong relationship between the two. So let's investigate. If we're trying to figure out the mean for this data, we simply multiply x times f, and we get the values that are listed here on the right. If we sum the rightmost column here, that's where this value of 2,203 arose. And this 900 comes if we sum the frequency column. So if we sum all of these values, we will get 900. And the mean is simply the division of all the data added up divided by the number of data given. So in this case, we're going to get a value of about 2.4478. So that's the ideal number of children. Now, of course, if we were to interpret this value, we're not going to say 2.4 because we don't have 0.4 of a child. So think about how you might want to deal with decimals when it's a real world situation of discrete objects. Also, we can calculate the standard deviation. We've done it before. And again, in order to relate this to probability, we're assuming that we have everything. So we're going to assume this is a population instead of a sample to make the calculations function in a similar way. So if we do a calculation for the standard deviation for a population, then the following would arise in the Excel spreadsheet. Now you've done this Excel work in the numerical Unit 2 Excel lab, and this one was for tuition. So the tuition example is exactly the same as the calculations I used for this example. The only thing that's changed is the data here in the front, the data values and the frequency. The rest of these are obtained by doing the same data value minus the mean, taking that previous column and squaring it, and then taking this previous column and multiplying it by the frequency to get this final total over here. And then, of course, we sum up all of this values on this far right column, and that gets substituted into the numerator. And again, this denominator is just the sum of the frequencies right here. So that's where the 900 is. And we get a value of 0.83 as our standard deviation. Now, here is a drawing of the histogram. Again, remember histogram, the bars touch in a histogram because 0 is right next to 1 is right next to 2. So these values touching makes sense. And this is a relative frequency histogram for ideal number of children. So if you notice, the height of the bar corresponds to a percentage or a decimal. Now, keep your eye on this column here and see what will happen next. We only changed 2 things. That might have happened too quick. So here, this is a relative frequency histogram with relative frequency. Now keep your eyes on the values. If we go to the next slide, I've changed a few words. And the words I've changed is the relative frequency histogram is now called the probability histogram. And the relative frequency over here is now P of X. So that's how you would say this. It's the probability of that data point. So relative frequency and probability are calculated in the exact same fashion. Now, why is that so powerful? Because it allows us to figure out the mean and standard deviation, and it also allows us to create a probability distribution histogram and create random variables that have a meaning that's related to probability. So really interesting to note is previously the mean was calculated by taking the sum of X times the frequency, all divided by the sum of the frequency. And if you think about what the probability of X was, it really is just the frequency of that value divided by the total frequency gives us the probability. So this formula is exactly the same that we've been using, but now it's taken on a different form to match what the probability will look like in the table that we're provided. So the calculation, instead of being X times F, all summed divided by the sum of F, it'll be the sum of all of the data values multiplied by their probabilities and added together. Similarly, the standard deviation you can get by some manipulation of the previous calculations that we've done for group data, and you'll arrive at this result. And again, all of this can be done really quickly in Excel. So again, we are going to treat this data as a population. In this case, this is going to turn into a probability. So now when we try to find the mean of a probability distribution, we call it an expected value. Since we're dealing with probability, we don't actually calculate a value. We calculate what we think will be a value because of probability. So there's uncertainty here. So the expected value is a way of saying that when we're talking about probabilities, this is what we would expect to have happen, not a reporting out of what actually did happen as it was in the relative frequency. So that change in terminology is what happened, not the change in calculation. So here, as I said, the new formula had the data value times the probability. So we have the data here, we have the probability for each one here. We simply multiply across. The first one became 0 because the x value was 0 when we multiplied. Then we got 1 multiplied by 0.0333. That'll give us 0.0333. And so forth and so on. And if we add the entire right column, we get 2.4478, which should look very familiar because that is exactly what we calculated when we got the mean for the frequency table before. So they are very related. Again, I went through the computations for the standard deviation for the probability distribution. And here, again, it's this last step where instead of being multiplied by the frequency, we're just going to multiply by the probability. And that also reduces the fraction that would show up in the formula for standard deviation. Now it just becomes multiplying by the probability. And that gives us 0.83, which again is also familiar from the previous calculation. So I'm going to pause here and give you a moment to think about all of that. That was a lot of information. So let's go into an example. So here, instead of doing all of the work with the relative frequency, we're jumping straight to the probability distribution for X. In this case, we have the example problem of parental involvement. Suppose this is a random variable that represents the number of activities a parent of a 6th to 8th grade student is involved in. So X being 0 means that the parent is not involved in any activities, 1 being 1 single activity, 2 being 2, 3 being 3 activities, and 4 being 4 activities. And if we sum up all of the probabilities here, we'll get 1, which means no parent had a different value other than 0, 1, 2, 3, or 4. So let's dive right in. First off, we'll create a probability histogram. Again, the bars are touching. Along the horizontal axis at the bottom, you'll see the random variable values of 0, 1, 2, 3, and 4. And vertically, you'll see the probabilities graphed there. The most common parental involvement would be 3 activities because it's the tallest bar. So we can already make some interpretations. And if you think about skewness, this is a clear example of a histogram that is skewed left. So let's get into calculating the mean and standard deviation for the discrete random variable depicted in this problem. Again, these are the two formulas which you can complete easily in Excel. I encourage you to use Excel for all of this work. So diving right in, if we have the value X, we have the probability. This last column simply says to multiply the 2. And if we add up that column, we will arrive at the expected value. We're going to call it expected value because it's what you expect to happen in the long run. And here the value is 2.5 activities. Again, if we're dealing with discrete data, then likely when you report this result to someone, you wouldn't say 2.5 activities. Parents aren't going to be involved with half of an activity and leave. I guess it could happen if you think about time, but in this case, we're talking whole involvement in the activity. then which way would you report in terms of the expected value? And that actually is a really good question, right? Because 2.5 is right in the middle. Would you round down or up? Might depend on the situation. Also, in this way, some people could not necessarily lie with statistics, but gravitate towards an answer that fits their need better. All right, the last but certainly not least part of this example, again, is the really complex looking calculation because of the standard deviation just being more complex. And again, you could set this up in Excel where you have the data values for the random variable listed first, the probability following in the second column. Again, we're subtracting the expected value. We used to say subtract the mean. We would square it. So this squares that previous column. And then this last column takes the previous column of 6.25 and multiplies it by the probability. And this entire right-hand column added up gives you the value underneath the square root. And after you take the square root, you have your standard deviation for the distribution of the random variable. So that's it for this lesson. I'll see you in the next lesson. We're going to venture into one specific discrete probability distribution that's used quite frequently, known as the binomial distribution. I will see you over in that video soon.